So neon, of course, is 2p. So I'm just going to draw its valence electron. So we have 2s, 2p. So we know that it's a noble gas. So it's all filled in. So versus, so fluorine. I'm just filling this in kind of quickly. So fluorine, oxygen. I'll stop here. Oxygen. Maybe I'll do nitrogen. Ah. Oops. Drew a little long orbital there. All right. So what we're trying to emphasize here with our radius is, so if we start with nitrogen, we're still, this goes back to what are our valence electrons. So we're looking at the same outermost shells for all of these, right? We're filling up our n equals 2. So this means we're filling up now our p orbitals as we go across. And so, right, we have our 2p orbital. So we're just putting more electrons in there. So we're not expanding it, right? We're not adding any more onion shells. But what happens as we fill in those electrons? What do you think might happen? And think back to the general structure of an atom, where we have our nucleus that's positive. We have our negative electron cloud. We're filling it up with more electrons. So what do you think might happen? So it doesn't become negatively charged, right? Because you keep adding protons too. But if you're adding more negative charges in kind of the same shell, then you're going to have exactly this more attractive force. So you're kind of filling up your shell. And so that means that the radius is going to get smaller. Exactly. So we're filling it up. We have our electrons still in the same orbital. So we haven't added them far away. So this actually makes the shell kind of get smaller. So now we have a nice attractive charge between our positive nucleus, our negative electron cloud. So as we fill in that same orbital, that makes the radius smaller. So very good. So radius smaller. So you could just make the general trend that radius increases as you go this way. So across the periodic table. So kind of francium we expect to be the largest, since not only does it have 7 shells, right? 1, 2, 3, 7. So it has 7 onion rings, but also has just 1 lone electron, right, floating in that outermost shell. So it's going to be pretty loosely bound. And so this radius increasing, right, that kind of explains the increasing reactivity of compounds as we go down. So we kind of mentioned that as well. So another periodic trend is electron negativity. And so electronegativity. And I'll kind of put here electron affinity. So they're actually 2 different things, but they have really similar properties. So electron negativity, and here's the difference. So this is basically how badly does an atom want an electron in a compound. So pull of atom in a compound. And so basically what this means is we have fluorine over here. Let's look at fluorine's Lewis dot structure. So fluorine is just one away from completing its octet. It's also on that second row. So it really feels everything, right? So it really wants that electron. And so this means that fluorine has the highest electronegativity. So what we find is in an atom, right, fluorine is pulling a lot. So it's pulling that electron density towards it because it wants that octet really badly. So fluorine is most electronegative. So the difference with electron affinity is essentially the same thing. So it's metal plus an electron to give you your charged species. And so you're measuring in the gas phase. This is in the gas phase, which is also makes it slightly different. So you find it generally follows the same trend, but the funny thing is chlorine actually has a higher electron affinity, but you don't necessarily need to know that. What we do need to know is that, so fluorine is our most electronegative, or this side again has our most electron affinity. And so say we'll write a little note here that electron negativity increases. So it kind of follows the opposite of radius. Let me switch pens. Never know where to write these things. So increasing E negativity, increasing electronegativity. So as we go across, basically, and they get more and more full, and they really want that full octet. That's what leads to the increase of electronegativity. So over here, right, your alkali metals, they're going to have a pretty low electron negativity. That makes sense. They don't even want an electron, right? We're going to find that these are actually going to lose electrons and give them up to, these elements with high electron affinities. So any questions about those? All right, let's go ahead and end there for today. I think we covered a lot. So for recitation, we'll probably do just focus on practice. We can also look at the labs too. But I definitely want to go over more isotope practice and then maybe touch on ions during recitation, since so far we've just been looking at a lot of neutral compounds. All right, any last minute questions? All right, thank y'all for an awesome stream. I know it was a jam-packed information session. This should hopefully help the next chapters go down more easily too. All right, so thank y'all. So we'll go ahead and end it here for today. So I could cover first and second ionization potential really quickly. I can't remember if it's officially in our book, but I'll just let people know that this is where we're kind of officially ending. And then ionization potential we can cover right now really quickly is kind of extra. So ionization energy. So if you have to leave, I understand. And I'll see y'all later today. So I'll do a quick ionization energy. So ionization energy is now kind of the opposite of electron affinity. So basically you have your metal plus some sort of energy. So for first ionization energy, so first ionization is just how much energy does it take to remove that first electron. And so if we look at ionization energy, what we would expect then is, so maybe you can tell me, so which elements are we kind of getting the sense that they want to lose electrons? Kind of highlighting them. Yeah, group 1, group 2. So all these, right, they're happy to get rid of an electron. And of course, so we'll think back to our radius. So this is going to have our lowest ionization energy compared to lithium, right? Since its valence electron is way out there, so it's easy to kind of pluck that off. Versus, lithium, again, still relatively easy, but since it has, only 2 shells, it's still held a lot closer to the nucleus. And then what would you expect it to do as you go across and you start filling in those electrons? So we were talking about the radius getting smaller. So if the radius is getting smaller, exactly, it's going to be increasing as we go across. So everything's kind of related. So we'll put decreasing ionization energy. Then as we go across, increasing ionization energy. And so you can imagine, right, by the time you get to fluorine, it's not going to be happy about giving up, any sort of electron. So now going down to second ionization. So the key is you're starting with now your M plus. And now you're trying to see, all right, what's it going to take a second electron off? And so in general, your second ionization energy is going to be higher than your first. So they follow kind of the same pattern. And so your ionization energies just kind of keep going on and so forth. And this is kind of, again, beyond the scope of, I think, what we're going to cover in the class. But I'll point out this chart here. So what we kind of notice, so we have helium, right, with our first ionization energy, hydrogen. Then we go to helium. So it's second ionization energy. That was harder to remove the first. Let's see, what am I looking for? I'm looking for a jump here. Here we go. Here's what I'm looking for. So at our more successive ionization energies, you can tell basically where your valence versus your core electrons are. So looking at boron, so its ionization energies, 800, 2,400, 3,600, and then, whoa, look at that huge jump from your